Hi students. In this lecture, I am going to discuss problems from HC Verma. Let us see first one. See the question given. A long solenoid is fabricated by closely winding a wire of radius 0.5 mm over a cylindrical non-magnetic frame so that the successive turns nearly touch each other. What would be the magnetic field be at the center of the solenoid if it carries a current of 5 ampere? Let us see how to start it. Right, first write down the given data. See what is given. It is a long solenoid, closely winding, radius 0.5 mm. This is cross-section radius of the wire, okay? Wire radius is 0.5 mm. Next, condition given that successive turns nearly touch each other. So what would be the magnetic field, right? The center of the solenoid. Current is given, that is 5 ampere. What is now field strength at the center of solenoid? Suppose this is now solenoid. At the center, we have to calculate. So we are knowing that it is equal to mu naught Ni, right? Mu naught, it is known, I value given. Now we have to get number of turns per unit length, okay? And see how to get this one from this R. This is radius of the wire, okay? Then see how to get it. Suppose this is now wire, okay? And you can see this length, this is equal to 2R, okay? This length is 2R. If you are winding this wire on solenoid, you can see here, see carefully, in a length of 2R. If you take length 2R, in that length, we are having only one turn, right? Because this length is nothing but diameter of that wire which we are winding on cylinder, means on solenoid. That means in a length of 2R, only one turn is present, right? So it is now for 2R length, it is one turn. Then number of turns per unit length, how many, right? So what is R value? Half mm. That means 2R means 1 mm. So for 1 millimeter, there is one turn, right? In such a case, in 1 meter length, the number of turns will be. Then see what we get. Number of turns will be, it is 1 millimeter, 1 meter. It will be 1,000 turns, right? Or you can take this is now small n, which is number of turns per unit length. So 1,000 turns per meter. Okay. So therefore, B value, now substitute here, mu naught 4 pi 10 power minus 7, n value 1000, and I value it is a 5. Okay, now see what is the value. It is 4 5s 20. That means 1 0 comes there. Here 3 zeros, totally 4 zeros. Next, this is now 10 power minus 7. 4 zeros, this is 7 zeros, right? So remaining is now 2 pi. 2 pi 10 power minus 3 Tesla, right? See carefully. 4 pi 10 power minus 7, 10 power 3. Remain 10 power minus 4. 4 pi is 20. So 1 0. Remaining is 2. So 2 pi 10 power minus 3, right? So here main thing is how to get number of turns per unit length. So getting the idea is somewhat difficult. So basic thing is in a length of 2R, there is only one turn. If you get that idea, then we can get number of turns per unit length, right? Let us see next one. A tightly wound long solenoid has n turns per unit length, r radius r, and carries a current coil. Given number of turns per unit length n, radius is r, current is I. A particle having charge q and mass m is projected from a point on the axis in a direction perpendicular to the axis. What can be the maximum speed for which the particle does not strike the solenoid? Let's see how we are solving it. First of all, make a diagram for the given data. It is now tightly wound long solenoid. So I am taking now that length is into the board. So when we are seeing from this side, it appears as circle. Okay. Length is into the board. Now, see what he is saying. Particle having charge q, mass m projected from a point on the axis in a direction perpendicular to axis. For example, see this is now axis which is normal to plane of this board, right, and into the board. Okay. For example, project now like this vertical. Let us say when you are projecting vertically, we are knowing that magnetic field inside solenoid is along the axis. That means between B bar and V bar angle, that is 90. And we have learned that if angle is 90, it follows circular path. Okay. Suppose it is now following circular path like this. Just touching like this. Circular path like this in this way. That means this is now 2R, right? Now this 2R, if it is equal to small r, here small r is radius of the solenoid. In that case, just touching, okay, it is just touching. Then corresponding velocity, that will be maximum speed, right? And we are knowing that radius of that circle is mv by b cube, right? Radius equal to mv by b cube, that is equal to r. Then say what is the value of, is asking maximum speed, right? Okay. So from this v value, b q r by 2m. Right? See carefully. V. This is maximum, that is equal to VQR by 2M. Now in this, you can see B value. Inside solenoid, B equal to mu naught Ni, right? Substitute that here, mu naught Ni Q R upon 2M. Okay. So only condition is now it is 2R should be less than or equal to. Equal to means it is now limiting value, right? Means it is now just touching, right? That's why we have taken it is equal to. So finally, what is the answer we got? Mu naught Q N I R by 2M, right? Now see the next question. A tightly wound sunlight of radius say length L has n turns per unit length. It carries an electric current type. Consider a length dx of the solenoid at a distance x from one end. This contains n into dx turns and may be approximated as a circular current I into n dx. Right? The magnetic field at the center of the solenoid due to this circular current. Integrate this expression under proper limits to find the magnetic field at the center of the solenoid. Verify that if L is very large compared to A, field tends to mu naught Ni, and if A is very large compared to L, field tends to mu naught NIL by 2A. Okay, let us see now. So condition given here, long solenoid. First of all, focus carefully. It is given length is, it is not long, it is length is L. Okay, number of turns per unit length is N. Length L, number of turns per unit length, that is N. That is current type. Right, now see first what he is saying. Consider a length dx of solenoid at a distance x from one end. Let's see. Suppose this is now solenoid. So this is solenoid. Let us take now from one end. Condition given that from one end. Take at a distance x. So I am taking here from this end at a distance x. Now we are taking a small thickness dx. This is now dx length. And we are given in a length means it is n is number of turns per unit length into dx. That gives number of turns. Right? Right. Now see what he's asking. Write the magnetic field at the center of the solenoid due to this circular current at the center. For example, this is now center. Assume that this is now center. Okay. Now see what we can write. Means how to calculate. This is now axis. At center because of this coil. Okay. That means it is now just like this point is on the axis of a circular wire, right? Then expression is, so we have learned that B equal to mu naught NIR square upon 2 into R square plus X square. To avoid confusion, I am writing here y square whole power 3 by 2. Okay, then see what happens. Distance of this point from center of this ring. Okay, that is now L minus X. Sorry, L by 2 minus X. Okay, so that I have taken as Y, right? Therefore, because of that, so I'm taking this as dB. Because of that, only small one coil, that is equal to mu naught in the place of number of turns. It is N into dx, number of turns into Y, that is a current, R square upon 2 into R square plus Y value L minus X, so Y square. So L minus X whole square whole power 3 by 2. This is now strength of the magnetic field at this point because of this coil. Now, see next point what he's asking. Integrate this expression under proper limits to find the field at the center of the solenoid. So like this, we have to consider all circular coils. Okay. Then see what we are doing here. Let us consider this. I am showing now this N2 center. Suppose that makes an angle. So take it as theta. Okay. Then what I can do is, in this diagram, tan theta equal to, so tan theta equal to R by L minus X. Or from that I can say L minus X is equal to R cot theta, right? So now here what I'm doing is I want to eliminate X. Okay. So I want to write in terms of angle. Then see what happens here. To get dx, we have to differentiate now this one. Okay. So differentiate that minus dx, that is equal to derivative of cot. It is minus cosecant square. So it is minus r cosecant square theta d theta. And in the place of L minus x, write r cot theta here. R square plus r square cot square theta. So now see what we are going to get. So I'm substituting these values in that. dB equal to mu naught NIR square. In the place of dx, I am writing here. See minus gets cancelled. In the place of dx, r cosecant square theta d theta upon 2 into, so here r square plus r square cot square theta. It is r square cosecant square theta whole power 3 by 2. So it becomes now 2r cube cosecant cube theta, right? Now see calculation. r square and r cube gets cancelled. Cosecant square, cosecant cube. What else left? Mu naught ni upon 2 cosecant 1 by sine. It is a sine theta d theta. This is now dp. Now integrate. Okay. Then see what I can do here. B equal to mu naught ni by 2 integration of sine theta d theta. So here you can see we should take all circular rings from this end to up to this end. Okay, that means this angle. If you join this point to this end, then corresponding angle, or I can take like this. This is now solenoid. So when we join midpoint of solenoid to the right end, suppose that makes an angle theta 1. So that makes angle theta 1. Okay. Next, join this end to that one, and that makes angle theta 2. Okay. Then I can write theta 1 to theta 2. That means we include all circular rings, right? Then see what we get. It is minus cos theta. Now take limits. This is a cos theta 1 minus cos theta 2. Since we have their minus, I have reversed limits. Okay. This is now expression. Now coming to, so this is in terms of theta 1 and theta 2. Right. Now see what is asking here. First assumption, verify that if L is very large compared to A. Here A in the sense it is radius. Okay. We have taken here capital. It is actually given as A. This is A. So first condition, if L is very large compared to A. See what it means. It means it is a long solenoid. Okay. Right. Now see what happens. B equal to mu naught ni by 2. Right. Now see what is theta 1. When it is a long solenoid, this theta 1 becomes now 0 because this end will be at infinity. Right. Otherwise, we can write like this. See here what I am writing. In the place of cos theta 1. Cos theta 1 is equal to cos theta. It's inside how much? It is L by 2 upon hypotenuse square root of A square plus L square by 4. Okay. Right. Next, see what about theta 2? Cos theta 2. We can see now this remaining angle is, see in this total value theta 2. Remaining will be 180 minus theta 2. Okay. So cos of 180 minus theta 2. Cos of 180 minus theta 2. That is equal to, see how much? Again, same value, right? eccentricity L by 2 by hypotenuse. That means this is equal to cos theta 1. Okay. That means cos theta 2 is equal to minus cos theta 1. Right. That means cos theta 1 minus cos theta 1. It becomes 2 cos theta 1. So I hope you got the calculation part here. Now 2 gets cancelled. In the place of cos theta 1, substitute this value and take assumption L is very large. When L is very large, L square will be very large. Therefore, we can neglect a square. When we neglect a square, remaining is only L square by 4 under root. That means L by 2. L by 2, L by 2. That is 1. So this is mu naught Ni. Or directly you can say theta 1, 0. Theta 2, 180. Okay, directly. Next, coming to the second assumption. Second assumption, if A is very large. Okay, now see in this what we have tried. Now this will be negligible when compared to A square. So remaining is only A square, root of A square, that is A. So cos theta 1, L by 2 by A means L by 2A, right? Substitute here in the place of this one L by 2A. So mu naught Ni L by 2A, right? This is what we have to prove, right? So in case of long solenoid, this is the result. This is now general one, okay? So this you can remember mu naught Ni by 2 into cos theta 1 minus cos theta 2, right? Let us see next one. Let's see the question given. A tightly wound long solenoid is kept with its axis parallel to a large metal sheet carrying a surface current. Condition is long solenoid is kept with its axis parallel to a large metal sheet. Surface current through a width dl of the sheet is k into dl, right? And the number of turns per unit length of solenoid is small n. The magnetic field near the center of the solenoid is found to be zero. That means field because of solenoid and that of this surface current both are adding to zero, right? That means both having same modulus value, right? Find the current in the solenoid. So just now we have seen that for long solenoid inside B value mu naught Ni, right? Next, if the solenoid is rotated to make its axis perpendicular to the metal sheet, what would be the magnitude of the magnetic field near its center? Let us see how to get it. First of all, make a diagram for the given data. It is given solenoid with its axis is kept parallel to a large metal sheet. Let me take this as a large metal sheet. Large metal sheet. We are placing here one solenoid with its axis parallel to that large metal sheet. Okay. And we are knowing that field inside solenoid is along the axis. And because of large metal sheet carrying surface current. Let us focus because of this how to find field. So we are taking a large metal sheet which it carries surface current. For example, it is now towards us. It is surface current. Condition given that you can see in a width of dl of the sheet, current is K into dl. So first I am taking an Ampere's law to find the field because of this. I am taking here a rectangle of length dl. This is now dl. Okay. In this dl length, current is now K into dl. So here by symmetry, see this is actually combination of infinitely long wires. I am repeating. This surface current. This can be taken as combination of infinitely large wires. And that length is now normal to this board, means into the board. Okay. So what happens is the resultant field will be only parallel to sheet and uniform. Okay. So here what I am taking is a loop is like this. Here current is now towards us. So keep the thumb of right hand towards us, curl fingers. Now curling fingers are anti-clockwise. That's why I'm taking here for the loop anti-clockwise as positive, like this. Anti-clockwise. Now see what happens. Since current is outwards, below this one, field is right side, above field is left side. Now apply Ampere's law. This is a DL and B value right side. DL bar and B bar both are in the same direction. Therefore, it is a B into DL. Coming to here, angle is 90. So it is 0. Because B bar dot DL bar, B into DL into cos of the angle. Cos 90 is 0. Next, coming to here, it is again B into DL. So write 2. Okay. B into DL. It is again here angle is 90. It is 0. So totally equal to mu naught into current, and current is K into dl. That is what given right in the question. From this we can write B value. It is mu naught K by 2. Okay. So now because of this in field is right side, because of this field must be left side. Both have same modulus values. So I'm equating now mu naught K by 2 should be balanced by mu naught Ni. Okay. So from this we can write current. Mu naught gets cancelled. I equal to, it is a K by 2n, right? See carefully, mu naught. I equal to K by 2n. That's the first part. Next, if the solenoid is rotated to make its axis perpendicular to the metal sheet, what would be the magnitude of the magnetic field near its center? Right? Then see what happens. Values are same, but now angle becomes between them 90. Therefore, resultant will be, it will be root 2 times mu naught K by 2, right? Because both are same, but now angle becomes 90. Okay, that's why root 2 times that value. So this is now mu naught K by root. Okay, let us see the next problem. See what is given. A capacitor of capacitance 100 microfarad is connected to a battery of 20 volt for a long time and then disconnected from it. Say given connected to battery for long time, it means capacitor is fully charged. That means across the battery, potential difference is 20 volt. Okay. It is now connected across a long solenoid having 4,000 turns per meter. It is found that the potential difference across the capacitor drops to 90% of its maximum value in 2 seconds. Estimate the average magnetic field produced at the center of the solenoid during this period. Okay, so first focus the given data. So write down that capacitor, capacitance 100 microfarad, micro 10 power minus 6 farad connected to a battery. So initially potential difference I'm taking as V1 initially 20 volt. Next number of turns per unit length given 4,000. Next potential difference drops to 90%. See 90% of 20 volt, that is 18 volt, right? And time taken how much? 2 seconds. Asking average magnetic field produced, right? See, we are knowing that B value mu naught Ni, right? Mu naught is a constant, N is a constant, right? But I is not a constant. If you want to find average B value, we have to find average current. Therefore, average B value that is equal to mu naught N into average current. Okay. So focus now how to get average current. So we have learned that average current is equal to how much charge flows in that given time interval, right? So Q by T. Let us see initially how much charge was there on capacitor Q1 C into V1, right? So this value how much? 10 power minus 4. 10 power minus 4 into 20 initial value. Final value 10 power minus 4 into 18. So how much charge has flown? That is a Q1 minus Q2. That is a 2 into 10 power minus 4. This much charge has flown in 2 seconds. Therefore, average current 2 10 power minus 4 upon 2 seconds, 2 gets cancelled. Substitute that here, mu naught 4 pi 10 power minus 7, n value 4,000 means 4 10 power 3. Average current 10 power minus 4, right? Then see what we get. Minus 7 minus 4 minus 11. This is now 10 power 3. Remaining is minus 8. So 16 pi 10 power minus 8 Tesla, right? See calculation 1, 16 pi 10 power minus 8 Tesla. Okay, that is the answer. So key point is that how to calculate average current. Then we get average magnetic field. Okay.